When you've got a sky like this, it's great to have a telescope like this. This is the 130 millimeter Newtonian reflector, and I'm about to tell you all about it. The way the telescope works is this. The light is coming from stars which are very distant, and it's very faint, and therefore I need a large opening, and this is called the objective of the telescope. The broader the objective, the more light the telescope can gather, and therefore the more faint and therefore more distant objects that this can see. This is a 130 millimeter mirror. If you looked down here, you would see that at the base of this telescope is in fact that mirror. So the light will enter the telescope, it will go all the way down to the mirror, which is a concave mirror. It's curved so that the light will converge to a focal point, and it will converge back up to a secondary mirror, which is approximately right here in the telescope. And that mirror is a flat mirror at a 45-degree angle, and it will cause the light to come back and then reflect right out through the eyepiece. And it's through this eyepiece that I'll be able to look to see the objects that I'm interested in seeing. So the light will travel the tube 2 times, all the way down to the bottom and back up. And that gives this particular telescope a focal length of 650 millimeters. One of the things that people always ask is, what's the magnification on that telescope? Well, really, magnification is not the issue. It can be worked out. So for example, the focal length of this telescope is 650 millimeters. If I use this eyepiece that has a focal length itself of 10 millimeters, I can do a simple calculation. The focal length of the telescope divided by the focal length of the eyepiece, which would be 650 divided by 10, gives 65. So the magnification using this eyepiece would be 65 times magnification. Changing the eyepiece to a higher value, so for instance, if this was a 100 millimeter eyepiece, focal length, then 650 divided by 100 would only be 6.5, so your magnification would go down. So the smaller the focal length of the eyepiece, the greater the magnification. But then let's talk about magnification for a second. We're talking about magnifying things that are trillions and trillions of kilometers away. Multiple light years. You're going to be looking at objects that are 100, 200, 1,000, maybe 50,000, maybe even 2 million light years away. And if you magnify something that is 2 million light years away, you're talking about a staggering number of kilometers that really can't be magnified. However, what you can do if you want to get a better look at it is you just get a larger and larger telescope. Like I said before, this one with a 130 millimeter objective mirror is good for a backyard astronomer, but the Hubble Space Telescope is a 2.3 meter mirror. 2.3 meters would be 2,300 centimeters, which would be 23,000 millimeters. This is obviously far bigger than this one, and as a result it can resolve better. It has a greater resolving power, and it can see much more distant objects simply because it has a much bigger objective lens. So you don't really talk about magnification when you're looking at a telescope. You're really talking about resolving power, and the larger the resolving power, of course, the larger the price tag. The first thing to take into consideration is the ground that it's sitting on. It has to be level. And of course, the reason we're doing it is because we want the telescope to think that it's part of the planet. So it has to be on a level surface to get a proper angle of view on the sky. So what we have right here on the tripod is a little window with a leveler in it, and we look at that bubble to make sure it's in the middle of the circle, and if it is, then we know that the tripod is sitting level. The next thing to take into consideration is the direction that the telescope is pointing. What we want is for the telescope to be looking straight north. And so what we do is we line it up, and right here on the telescope on the front of the tripod is the letter N for north. And as long as that's pointing in the right direction, then we know we're lined up properly. Of course, the reason for this is because the axis of the Earth also points straight north. It runs through the planet, right through the North Pole. And so we want the telescope to be lined up with that. The last thing to take into consideration is the angle that the telescope is situated at. What we want is an angle to be exactly the same as the latitude that you're at. Now we're at 49 degrees north of the equator, but picture yourself at the North Pole, 90 degrees north of the equator. Where would the North Star be? Well, it would be at your zenith. Your zenith is straight overhead. Wherever you are in the world, the zenith is straight overhead. So I'd have to have the telescope pointing straight up at an angle of 90 degrees to the horizon. Conversely, if I was at the equator at 0 degrees north, the North Star would be straight along the horizon. It would be right along the horizon, and therefore the angle of the telescope would have to be dipped down to be at 0 degrees to the horizon, or in other words, horizontal. So at the equator and the North Pole, it's kind of easy to picture if the idea is to line it up with the North Star. But when we're at 49 degrees north, it's not quite as easy to understand.
The Earth is tilted to an angle of 23.5 degrees, and this causes the axis of Earth to point straight at Polaris, the North Star. We're situated 49 degrees north of the equator. A triangle is 180 degrees, so the three angles must add up. 49 plus 90 plus 41 equals 180. Opposite angles are also equal, so the other angle must also be 41. Complementary angles add up to 90, so 41 plus 49 equals 90. And that's the angle that the telescope must be tilted at in order to face the North Star.
Well, now that it's gotten dark, this is obviously the prime time to be using a telescope. So let me show you a couple of things that you would do once you're outside with the scope all set up. First, one of the things you have to take into consideration is to take the lens cover, or in this case the objective cover, off for a good period of time, maybe half an hour. Believe it or not, the temperature inside the tube will be different than the temperature outside. And with that temperature difference, you will get a distortion. So the telescope, it does have to sit outside in the ambient temperature for a period of time. This telescope is really cool because it's got a brain. It can actually follow the motion of the planet, because of course the Earth is rotating. And at the rate that it rotates, you think about it, one rotation is 360 degrees, and it does so in 24 hours. That's 1,440 minutes. And when you divide 360 into 1,440, what you do is you get 1 degree of movement across the sky every 4 minutes. Now, what's a degree in the sky? Well, the full moon is about half a degree of angle in the sky. So if you're looking for a reference point, look at the full moon. That's about half a degree. Two side by side would make a full degree. So the gearing in this motor will actually turn the telescope at a rate of 1 degree every 4 minutes. So whatever it's looking at will stay in the center of the field of view. Without that, then every few minutes or less, you have to continue to adjust the position of the telescope, because the objects in the sky will continue to move as the planet rotates. So what we'll do is we'll give it power. So I've brought out a battery pack, which is required for this sort of thing, and I'll plug it in and I'll turn on the brains. And it's ready to start thinking. Now remember, earlier today I set the telescope up so that it was pointing straight north, it was level, and it was tilted at a 49 degree angle, because that's the latitude that we're at. And now I've just given it power with the brains of this particular telescope mount. I've keyed in the date, the time, our latitude and longitude, and I'm ready now to start a 3-star alignment. Now the reason you do a 3-star alignment is if I give the telescope the opportunity to see 3 different points in the sky, it will use triangulation to know exactly where it is. And from that point on, anything I ask it to find, it can do so because it knows exactly where it is and what it's looking at. The expression is slewing. We're going to allow the telescope to slew, and it's really cool. Check this out. Slewing. Now, according to the brains, the telescope is now looking at the great red supergiant Arcturus. All right, let's check it out and see if Arcturus is in the viewfinder. Perfect, dead center. So once the 3-star alignment is done and the telescope has stopped slewing, it now knows exactly where it is. It knows exactly what it's looking at, and it's ready to start hunting for deep sky objects. So what do you want to look for? Let's start with Venus. Wow, so cool. Venus just looks like a little white dot in the sky, but through the telescope, it's this crescent. It looks like a little tiny crescent moon. That's so cool. What else should I go hunting for now?